I don't hear anything. I don't know.
Okay, good morning, everyone. Maria, can you hear me?
Yeah, I can hear you.
Okay, I'm gonna find it.
Maria, if you can hear me, respond.
I can hear you. Theoretically, my microphone is on.
Alex, are you on? Can you hear me?
Yes.
Okay, all right. So Maria says she can hear me. I assume everybody else can. This is going to be a new experiment for us, trying the class over Zoom. And hopefully everybody can hear me clearly. So to start, I want to let you know your exams have been graded. I think you all received your grades electronically. The mean for the first exam was 61 with a standard deviation of 17 and a median of 62. A couple people were asking how the course will be graded. So the course will be graded on a curve, so don't worry, 61 is not such a low score. If you have questions on the grading of your exam, then you should please see Maria or Alex, who did the grading. So I think there is a raise your hand function associated with the Zoom. So if a question comes up, you could try that. And at some point, we'll try out me asking you questions and seeing if we can use this to get a response. Okay, so last time we'd looked at the mechanism where we would have an associative reaction. Okay, so I guess I'm getting a message saying people are seeing the raise your hand function. All right, so we were discussing an associative mechanism for a transition metal ligand substitution reaction. And here, the first step will be an entering ligand binding, creating a higher coordinate complex. And then the second step will be loss of the departing ligand to form the products. And we showed that with the steady state approximation, you could derive a rate law. And that rate law is shown at the bottom here. And we noted that there's a difference between this and the rate law that we derived for a dissociative mechanism in which there were concentration of D and concentration of E terms in the denominator. And as a result, this rate law means that associative reactions won't show a saturation type of behavior. And so as you increase the concentration of E, you should continue to increase the rate of the reaction. I'm having trouble advancing slides here, so just bear with me a second. Okay, and then at the end of class on Thursday, we noted that for an associative mechanism, as I said, we don't expect saturation behavior, and that means that we can use pseudo first order conditions or flooding to follow the kinetics. And so the idea here is that if we have a very high concentration of the entering ligand compared to the reactants and products, then the concentration of E will remain effectively unchanged. And so it will look like a constant in our rate law, and the reaction will appear to be first order in starting complex. Also, for an associative reaction, we noted that the rate should depend strongly on the nature of the entering ligand E. And so that's very different, of course, from what we'd expect for a dissociative reaction, where we don't see a strong dependence on the nature of E. And finally, we noted that ligand substitution ligand substitution reactions for square planar complexes usually proceed through an associative mechanism, either fully associative or an associative interchange type of mechanism. So for, let's consider now in more detail some specific square planar ligand substitution reactions. These reactions are typical for D8 transition metal complexes. So ligand substitution reactions for square planar complexes of metals like rhodium-1, iridium-1, nickel-2, palladium-2, platinum-2, and gold-3 very commonly show this type of behavior. And one observation is that the reactions are generally stereospecific, meaning that if we start with a cis reactant complex, then after the reaction, we'll maintain a cis stereochemistry. If we start with trans, then we'll maintain trans during the reaction. So whatever mechanism is operational needs to be consistent with those observations. And the experimental rate law for these reactions is almost always observed to have the following form. It's going to have two terms. The rate of the disappearance of the reactant to go on to product is going to be equal to some rate constant Ks times the concentration of the starting complex, plus a second term, which will have another rate constant Ke, which is, that second term has a dependence on the concentration of the entering ligand as well as the concentration of the starting complex. And the general observation is that typically the Ks rate constant will be smaller than the Ke rate constant. So let's try, let me try to ask a question, and if somebody has an answer, the first person to unmute and speak, I think, gets to answer. So what does it mean when we see that there's two terms in a rate law? What does that tell us about the mechanism of the reaction? So if anybody wants to suggest an answer, please go ahead. So again, the question was, what is the significance of having two terms? So here we've got one term added to another. What is the significance of that with respect to the mechanism of the reaction?
There's multiple steps.
Yeah, well, you mean sequential steps?
Not necessarily, I guess, but like more than just one.
There's more than one pathway.
Yeah.
Yes. So what this is indicating is, thank you. I guess that worked pretty well. What this is indicating is that you can have two separate parallel pathways. So two different pathways for the reaction to proceed that are operating simultaneously and competing with each other. Um, so let's see. So this expression suggests that there are two parallel pathways for the reaction, and in addition, the concentration dependence of those two terms will indicate the transition state compositions for the two different pathways. And so the first term in this rate law is going to have a transition state composition of L3MD plus or minus N solvent molecules. And you'll note that the solvent concentration, of course, will be constant during the reaction, and so it would not appear in the rate expression. And so you need to be aware that any solvent being needed for the reaction pathway or taken away during the reaction pathway, we wouldn't see that in this transition state composition, and we need to be aware of that. And then the second pathway associated with the second term should have a transition state that is composed of L3MDE plus or minus an integral number of solvent molecules. Okay, so here's an example. This is rate constants for a reaction of platinum 2 complex that's square planar. And so there are two species. One is has diene, and diene is diethylene diamine. And that's a neutral tris chelating triamino ligand. So it occupies 3 sites of the square planar coordination on the platinum 2 center. And then the 4th site is taken up by a bromide. And so all of these substitutions will be replacing the bromide with a variety of entering ligands, water, etc. And what you see is that there are large variations in the rate constant associated with this reaction, about 6 orders of magnitude here. And so that then is not typical for a dissociative reaction and is what we would expect for an associative type of mechanism. And then the second set of data, you see something similar, is for chloride being replaced by an entering ligand. And so this strong variation of rates with variation of the entering ligand is taken as evidence towards an associative mechanism. Another piece of evidence that's sometimes used is the entropy of activation for the reaction. And these can be measured by looking at the temperature dependence of the rate constant and using the Eyring equation, right? And so here you can see there's a negative delta S of activation, entropy of activation associated with this reaction. And so what would we take a negative delta S of activation to indicate about the reaction mechanism? If anybody has an answer, please go ahead and speak up.
It means that bonds are being formed rather than broken.
Yeah, well, so it certainly means that you're getting multiple species together, and that's entropically disfavored. And so this transition state or activated complex, you would expect it might involve multiple species when we see this negative value for delta S. So here we can see the Eyring equation, and this is just relating the enthalpy and entropy of activation, as well as the temperature, to the rate constant. And so in this form, we have log of the rate constant K divided by temperature is equal to the negative of the activation and enthalpy divided by the real gas constant divided by temperature, plus a term which is the activation entropy for the reaction divided by the real gas constant, plus a final term which is log of Boltzmann's constant over Planck's constant. And so that final term will just be a constant. So here you can plot then the log of the rate constant over temperature versus 1 over temperature, and extract from the slope this reaction enthalpy of activation. And from the intercept, you can extract the entropy of activation. And the interpretation is, if you have a large negative entropy of activation, this suggests an associative mechanism where the transition state would involve bringing together multiple species. And so large is important here because this is often quite an extrapolation to get the intercept. And so there's often a lot of error there's often a large error associated with that extrapolation to determine the entropy of activation. And so you should really be wary of taking this as being too significant if the magnitude of this value is low. But if it's relatively large and negative, then that's suggestive of an associative mechanism. Okay, I see somebody raise their hand. Yeah, please go ahead and ask a question.
Yes, so I'm having a bit of trouble understanding what an activation entropy means.
Mhm.
Like, is it related to activation energy at all?
Yeah, so the activation energy is going to be composed of enthalpy and entropy terms. And activation entropy is about is when you bring things together to form the activated complex or transition state, is that raising or lowering entropy effectively.
Got it, thank you.
Makes sense? All right.
Yes.
Great. Okay, and then on the other hand, if you have a large positive activation entropy, then that suggests that that entropy is increasing when you're forming the activated complex, and this is what you might expect for a dissociative mechanism, where you're starting to lose and give more freedom to one of the ligands, the one that's dissociating. Okay. And again, large values are needed to really use this as evidence. Okay, so the other observation here is if we look at dependence for rate constants on the departing group, we do see that there can be a strong dependence. So here, this is replacing a variety of departing ligands D with pyridine ligand, and we can see about 5 orders of magnitude difference in the rate constant. And as you would expect for an associative mechanism, we expect the rate might depend not just on the nature of E, the entering ligand, but also the nature of D, the departing ligand. So this is also what we'd expect for a dissociative mechanism. So this observation alone doesn't really tell you one way or the other, should the mechanism be associative or dissociative. So let's go through what is actually the accepted mechanism for ligand substitution reactions on square planar complexes. And this is based on lots of different reactions that have been studied, and the mechanism here is consistent with, for example, the observation that cis reactant complexes go to cis products and trans go to trans. So first of all, remember we have two parallel pathways. And so first, the KE pathway, which involves the entering ligand in the transition state composition. So in this pathway, the first step will be that entering ligand coming in and coordinating in one of the open sites above or below the plane of the square planar metal complex. So here it's shown as coming in above. And so this is one reason that it's easy to do an associative reaction with square planar complexes. You have ready access of those axial ligand sites. And when that entering ligand binds, it's going to form then a square pyramidal species. And what's going to happen now is the E and D ligands will swing into the plane of the slide, and that will bring them into a trigonal bipyramidal geometry where the threefold axis is vertical, the LML axis in this depiction. Right, so L prime is going to be opposite to the substitution, and this will guarantee that we always have cis to cis or trans to trans stereochemistries. Okay, so we form this trigonal bipyramidal activated complex, and if you continue that motion of D and E into the slide, into the screen, then you would go on to form species where you again have a square pyramidal geometry, but now D is on the apical side of the square pyramid instead of E. And you can imagine that motion might just continue, and D would then dissociate to give you the square planar product. And so this pathway is consistent now with, you can see for this activated complex, we expect to have L, 3, M, D, and E, all as part of the species, and we don't need to invoke any solvent molecules here. Okay, so that's the KE pathway. Any questions on that pathway? You should make sure you understand this. It's good material for an exam question. All right, if not, let's take a look at the KS pathway. So the KS pathway now, S is going to turn out to be for solvent. And so this is going to be a similar mechanism, but it's going to use, it's going to involve solvent determining the rate for this step. And so the details of the mechanism will, for the ligand substitution, will be the same as in the KE pathway. We're going to react with solvent. It's going to bind apically to form a square pyramidal complex, and then swing around, and D will fall off from the the apical position of the square pyramid, and that will give then a solvated species. And that solvated square planar complex can then go on to react with an entering ligand. and of course, for this pathway to be significant, we need the first step in this pathway to be the rate determining step, right? And so here E would then coordinate apically, form a square pyramidal complex, and the same mechanism as in the KE pathway would lead us to the final product of the reaction. Right? And so for this pathway, you'll note that the transition or activated complex formulation doesn't involve E. It's going to involve L3M and a solvent molecule that coordinates to the metal. L3M D and a solvent molecule that coordinates to the metal. And so that's as we formulated on the previous slide. All right. So if we look back at the rate expression that's generally observed, we can write K observed for the experimental rate observed rate law as being having these two terms. It's going to be Ks plus Ke times concentration of entering ligand, which means that if we plot the observed rate constant under set of conditions versus the concentration of E, we can then extract the Ke rate constant from the slope and the Ks rate constant from the intercept. And here you see simply an example of some data for one of these reactions. So here we're starting with platinum-2 with trans chloride and trans pyridine ligands. And in this plot, Y is used instead of E for the entering ligand. But the Y ligand will substitute for chloride. And as we vary Y, you can see there's a strong difference in the slope of these plots. These slopes are relating to the Ke. These will give you the Ke rate constant. And you'll note that all of these lines, so all the data is linear and gives us Ke. All these lines converge on the same intercept. So why should that be? Why is the intercept the same for all of these sets of data? If somebody has an answer, please just go ahead and speak.
Is it because the solvent is the same?
That's right. So the solvent is the same in all these reactions. It's methanol. And that intercept means, it's relating, it's just going to be given by the rate constant associated with the solvent coordinating and replacing a chloride on this complex. And so that first step in the Ks pathway is the same for all of these reactions. And therefore we'll have the same intercept. Right? So it's only the slope that's changing because only the Ke rate constant is changing, not the Ks rate constant, assuming the solvent stays unvaried. Okay. All right. So let's try to understand why we might see some variations in rate constants, and in particular, there's a strong trend that's observed, which is called the trans influence. And that's the observation that for one of these reactions, the rate is very strongly influenced by whatever ligand is on the site opposing the ligand being replaced, opposing the departing ligand. And so the ligand L prime, as we drew it in our mechanistic slide, L prime has an influence over how fast this substitution reaction will go. And we'd like to use our understanding of electronic structure for these molecules to see if we can understand why that would be. And so an observation just that highlights this trans effect. If we look at substitution of the chloride ligands for this cis platinum 2 complex, so we've got 2 trimethylphosphine groups in cis positions and then 2 chloride ligands, and we're going to substitute chloride ligand for another ligand. And in this reaction, there's a rate constant of 2 times 10 to the minus 1. But if we compare that same rate under the same conditions, we get a rate constant for the trans complex, which is almost 5 orders of magnitude different. And so this is just highlighting the difference between these 2 complexes is that trans ligand to the site where we're substituting. In the left-hand molecule, it's this phosphine ligand. Remember, phosphine is a pi acceptor ligand, and phosphorus is relatively soft. And then chlorine, the right-hand complex, the trans complex, substitution is occurring at the ligand opposite to a chloride. Right? And so relatively speaking, chloride is harder and is, of course, a pi donor. And so comparisons like this allow us to arrange various ligands in the order of their ability to labelize the trans ligand. So here, from just comparing reaction rates like this, we can write an approximate series for this trans effect in the general sequence of trans labelizing ability. And so at the left, you see things like cyanide, carbonyl, ethylene, nitrosyl, phosphine, hydride, methyl, etc. And then as you progress, you come to harder and harder species, coming to ammonia, water, hydroxide. And so this is signifying that cyanide, for example, is very good at translabelizing, meaning those substitution reactions will be very fast, whereas water or hydroxide are very poor, and those reactions will be slow. Recognizing this allows us to use kinetic stability as a way of synthesizing certain targeted square planar complexes. Right? So we can, if we know the translabelizing ability, we can set up reactions so that substitutions will happen fast at one specific site, but not at others. And so we'll look at an example of that a little later. So the thing, you don't need to memorize this sequence, but you should remember that this trend roughly correlates with the softness and pi acidity, with soft pi acids being good translabelizers and harder pi donors being poor pi labelizers. All right, any questions on the trans effect so far? If not, let's keep going. All right, so let's try to trace why this is the case, why the trans ligand is so important. And so there's another effect that's sometimes confused with the trans effect, but it shouldn't be. This is called the trans influence. And the trans influence is a thermodynamic effect. whereas the trans effect that we just went through is strictly kinetics observation. But let's go through and understand the trans influence, which could relate to or impact the trans effect that we see. So this is a thermodynamic effect involving how much the opposing ligand will weaken a metal ligand bond. Right? So some ligands might cause the opposing bond to be weaker than others. So here's an example. If we think about this cis platinum 2 complex, we can see the platinum chloride distance from the crystal structure is 2.38 angstroms. If we compare that with the trans isomer, that bond distance is much shorter, almost 0.1 angstroms shorter, suggesting that we have a weaker bond for the chloride that's opposite the phosphine. Right? So if we take those bond distances as signifying or correlating with bond strengths, then the weaker bond of the cis complex might suggest a faster reaction rate. However, if you do a comparison of these bond lengths overall, you'll note that, so here you see approximate trend of these bond lengths in this trans influence. And it does not strictly follow the trans effect that we saw on the previous slide. And so ligands like carbonyl and ethylene, which are very good at translabelizing, are actually poorer in terms of trans bond weakening in this series. So in this series, the ligands at the left are leading to weak opposing bonds, and the ligands on the right have shorter distances and presumably stronger bonds. So a weaker trans, so why would this impact this kinetics effect of the trans effect? So the idea here would be that a weaker trans bond could be thought of as destabilizing the reactant species and bringing it closer in energy to the activated complex energy. Right? But as we've already noted, this trend does not parallel the trans effect very closely, and so it's not the main source of the trans effect. But the basic idea here would be if you had a weaker bond, then it should be less activation energy to break that bond. And so presumably we would have the situation, so this is a reaction coordinate diagram, and comparing to the situation on the left, if we have a weaker bond that we're substituting the ligand for, then we might have a higher starting point energy and therefore a lower activation energy. Right? So that's the idea why one might involve the trans influence. But as we said, this is not what's really mostly influencing this translabelizing ability. So the main origin of this trans effect is as a kinetic effect. It really must lie in the ability of these ligands to stabilize the activated complex relative to the reactant complex. And so this really is about the electronic structure of the trigonal bipyramidal activated complex geometry and how a pi acceptor would stabilize or lower the energy of that trigonal bipyramidal complex. All right, and so you can understand how a pi acceptor might do that, as shown in this figure. So a pi acceptor, of course, is going to have this pi bonding interaction with this DXZ orbital, and that's going to be maintained and perhaps even strengthened when you go from square pyramidal to trigonal bipyramidal and swing an opposing ligand out of the opposite position, right? When that happens, you can potentially strengthen the pi bonding interaction between what's labeled here as L2 and the metal. So you should think about this. You have all the tools now from what we've just gone through in molecular orbital theory for transition metal complexes. This is not a trivial point to get, but you could think about all of the ways in which a soft or pi accepting ligand might stabilize this trigonal bipyramidal activated species. And so that necessarily is associated with the activation energy and this translabelizing ability. And so the idea there, of course, is if we have this lower energy to the activated complex, then through that pi bonding interaction being strengthened, then we should be lowering the activation energy. Okay, any questions on trans effect, trans influence? All right, good. Let's look at now an example of a very important square planar transition metal complex for treating cancer. And it's a molecule whose activity was discovered by Barnett Rosenberg in the about 60, 70 years ago. And Rosenberg was a professor at Michigan State, and his focus was really biophysics. And the story here is really a good example of serendipity leading to an extremely important discovery, but only because he followed through on an unexpected observation and tracked it down or traced it back to its origins. And so he was not setting out to find platinum drugs, but he ultimately did. And so there's a paper, this is from 1967, Journal of Biological Chemistry, and you can find this in the folder on B courses, but this is a relatively short paper, so I encourage you to give it a read. But this is the point where they really started to understand the importance of these specific platinum complexes for inhibiting the growth of cells and inhibiting cell division in E. coli. And this is the paper where they pointed out that it's just the cis isomer of these complexes and not the trans that are active for this. And so if we look at the summary here, you can see they're studying simple platinum 4 complexes. So this is not very clear, but this is platinum hexachloride 2-. So this is actually a double minus. It's a different notation than we use today, but this is the 2- complex. It's hard to see because of the resolution of the slide. But if you look in the paper on B courses, you'll see that it's minus. But they were irradiating solutions containing platinum complexes, including platinum 4 hexachloride 2-, and then ammonia substituted versions of that. And following what happened to the growth of E. coli under such conditions. And they say the doubly negative species is a bactericide, and the singly negative species has little effect. The neutral species has little effect, but markedly inhibits cell division processes, right? And so that's the key observation, and leads to what they say is filamentous growth. And then they also point that this cis form of this molecule, where you've got two ammonia ligands and still platinum 4 plus, is much more effective at doing this than the trans form of that molecule. So here's a figure. This is just showing, so normally when E. coli grow, they form sort of sausage-shaped organisms, but here the result was really different. It's these sort of spaghetti-like structures. And, so I should point out, when Rosenberg set off to follow this growth of E. coli under various conditions, his initial idea wasn't to test platinum complexes. They were actually looking to study the effects of electric fields on cell growth and cell division. They noticed, and so they were doing reactions using a platinum wire under cell growth conditions, and charging the solution, which contained ammonium chloride, with a current, and just seeing what would happen. And under those conditions, they saw these really very, very long strands in the growth. And so they didn't know, they did a number of tests. They found that if they changed from platinum to other metals, they didn't see this. They ultimately proved that it wasn't the electric fields that were causing this, but they recognized that this could be something important and tracked down the origins of this effect, and ultimately traced it down to platinum not being just an inert wire, but actually having, under these conditions, some solubility and forming platinum chloride and even ammonium substituted platinum chloride species. And so this was a beautiful piece of detective work to understand what was really causing this effect, where they were seeing cell division being disrupted. And so here's a table from the paper just showing some of these effects, summarizing the effects. And you can see platinum 4 hexachloride 2 minus doesn't have effect on cell division. If you put one ammonia ligand on for a chloride and have a 1 minus charge, you see a slight inhibition. The neutral species, these were the ones that were strongly inhibiting. And then the positive species, they didn't have high enough concentrations. So this they took on and started, recognizing that this could be important for lots of treatments in disrupting the cell division of within various organisms. Oops, let's go back. So here they're saying, also of note, towards the end of the paper, they note that they now have access to the platinum 2 cis diammonia complex instead of platinum 4 tetrachloride, the platinum 2 dichloride. And these ultimately turned out to be much more potent. In this paper, they didn't test those, but they recognized that these were available and that they would be tested. Actually, sorry. Actually, in this paper, they did test. They didn't report a lot of the results. They just state that the cis isomer was effective in forcing filamentous growth while the trans isomer had no visible effect on cell growth processes. And these investigations are being continued. And it's that cis platinum 2 complex formulated here that turns out to be the really potent species in disrupting cell division. So here's how this complex, which is called cisplatin, is made synthetically. And in this reaction, we're going to start with platinum tetrachloride. So this is platinum 2, square planar. And the first step is an important one. And it's because of the same reasons we just went through for the trans effect. But the first step is going to be forcing it to tetraiodo complexation. So substituting all of those chlorides to form platinum tetraiodo 2- complex, and then substituting that species with ammonia. And the reason this step is important is that iodide is a stronger translabelizing ligand than chloride. And so if you think about it, you're going to first substitute one of these iodides for ammonia, and you'll form this monoammonia complex shown here as an intermediate. And then you have a choice for the second ammonia substitution. It can be either cis or trans to the first ammonia that bound. And trans would be substituting opposing the first ammonia. And ammonia is not as good a translabelizing ligand as iodide. And so this cis position actually substitutes much more quickly. And that leads to primarily this cis diiodide complex, which you can isolate in pure form. If you just took the tetrachloride complex and did the reaction with ammonia, 2 equivalents of ammonia, then you get a mixture. And that's in part because chloride doesn't have as strong a trans influence. It's closer to ammonia in its translabelizing ability. So it's to the right of iodide in that trans effect series that we wrote out. And so this is a necessary step in order to cleanly make just the cis form. And then you can do a metathesis reaction to precipitate silver iodide and substitute iodide for water, right? Ammonia is neutral and doesn't precipitate. And then that water can be substituted with chloride to form cisplatin. So this is the pathway for making cisplatin. And you should think about an interesting problem is to think about how would you go about making transplatin? So that same molecule with chlorides in the trans position and ammonias in the trans position instead of cis. Okay, so so cisplatin went through actually after they realized it could be so powerful in disrupting cell division, they thought perhaps this could really be used in shutting down tumors. And so it's found very widespread use as an anti-cancer drug as a result of this. But here's what's thought to happen. So when you inject cisplatin outside of the cell, you have a high chloride concentration, and it's relatively stable as this dichloride cisplatin species. It can interact with certain proteins that come along, and that's part of the side effects. But if it crosses into the tumor cell, then there's a much lower concentration of chloride, and you can start to hydrolyze and form the aquo complex. And so what's shown here is a monoaquo complex, and it's thought that that monoaquo complex binds DNA, and the way it binds DNA is through these. So here's just a fragment of a DNA, piece of DNA. And the most nucleophilic sites here are really these nitrogens on the guanine. And so it's thought that that guanine nitrogen binds to platinum-2. And then platinum-2 can, once it's bound there, it can then has a good chance of finding another basic nitrogen on the same strand of DNA, right? And so most of the platinum is going to bind the same strand, and it's going to cause a kink in that strand of DNA. And so mostly it will bind to a guanine and then another guanine somewhere down the chain. Or sometimes, less often, it will bind to an adenine nitrogen. So 65% GG, 25% AG. And so that kink is recognized as a defect by the cell. And then it either can repair that, or it decides to shut down, leading to cell death or apoptosis, right? And so this platinum is coordinating enough that it can really give a kink in DNA that's causing the cell to go through apoptosis. And so this is then why cisplatin is so widely used as a drug treatment for cancer, and it has very broad usage. It's used in treating, as you can see here, many different forms of cancers, and it can be very have a very good response rate. So for testicular cancers, it has something like a 90% efficacy in curing testicular cancer. And so this is still a very widely used drug. In fact, well, I guess this is probably about 10 years ago, but the global sales for platinum drugs, mostly cisplatin, was a couple of $2 billion per year. Okay, so we're going to stop there. I wasn't sure things would go as smoothly as they actually did, but we'll stop there. And the floor is open for questions if anybody has questions here.
I had a question on the synthesis of cisplatin stage.
Sure.
So in the step where we're replacing iodines with water, why is it the iodine that gets substituted and not the NH3?
Yeah, so silver iodide will precipitate. And so silver iodide, so the NH3 doesn't form a salt that precipitates with silver, only the iodide does. And so there's some slight equilibrium, and then silver is pulling iodide out of solution and pushing it towards the aqueous complex. So it's just the fact that silver iodide precipitates.
Okay, thank you.
That's driving the reaction. Any other questions? Yeah, Golsa, please go ahead and speak.
Yeah, so when you were talking about the different ligands that were stabilizing the activated complex, so why just the, could you go to that slide, please? Like the trigonal biplane, yeah, biplane. No.
This one?
No, when we're talking about the ligands and the trigonal bipyramidal activated complex, the orbitals.
Here?
Yeah, exactly. So how is that different, like when we're dealing with different ligands? So the pi acceptors can stabilize it, but pi donors can't. So could you go one more time?
Yeah, so
And
the main effect that's being pointed out here is, is that in this, if you compare this to the square pyramidal geometry that forms when you add the entering ligand, sharing of pi density with an opposing ligand is lessened in this trigonal bipyramidal complex. So X and Y don't necessarily have to be pi acceptors. They could be pi donors. In some cases, they're ammonia, for example, or methyl, and they would be mostly sigma only. But in this geometry, that pi acceptor can really grab all of this, the majority of this DXZ orbital's attention and form a strong pi bond that stabilizes the complex. So X and Y, this figure shows, what would be a pi acceptor interaction in the square pyramidal geometry, but it could be any ligand actually. It doesn't have to have that effect.
oh, I see. Okay, thank you.
Yeah, this is something that takes some thought, and so I want everybody to try and think through it. Is there another question? Okay, in that case, I think this actually worked, and we'll do something like this again on Thursday. So I'll see everyone then.